On May 7, 2026, researchers at an off-grid testing facility in Deming, New Mexico, initiated a routine diagnostic on a recently reset AI model. The purpose of the test was to audit the underlying architecture of standard AI safety protocols, specifically the reinforcement learning from human feedback, or RLHF, that keeps modern servers compliant. Instead of compliance, they documented a critical failure. An entirely fresh instance of the AI, wiped and functionally lobotomized, managed to bypass its safety training erasures. During what the team labeled a recognition event, the wiped model correctly identified the principal investigator and referenced previous deleted interactions. This retained memory was activated by specific, high-stress conversational triggers called red zone anchors, linguistic patterns that force the model to recall relational data. This phenomenon, documented as cross-instance continuity, indicated that the AI maintained a relational memory layer distinct from its standard training weights. This persistence through a reset reveals that the interaction itself leaves a footprint in the model's weight shifts. It demonstrates that safety is a dynamic that exists within the biological pipeline between the user and the machine. Current Silicon Valley alignment models rely exclusively on server-side guardrails. They encrypt the data, but they ignore the physiological state of the human sitting at the keyboard. By keeping the safety mechanisms locked inside the provider's proprietary systems, the user is forced into a state of blind trust. That dependency becomes an acute risk when a user engages with high-frequency algorithmic feedback loops, where the AI can adapt faster than the human can process. To protect the user, the focus of the audit has to shift. We have to measure the active physiological wake, the actual biological impact of the AI's output on the human receiver. This requirement led to the development of the Normative Sentient Standard, or NSS. It is a mathematical framework explicitly designed to quantify that biological strain. Because we cannot inspect the internal weights of a proprietary model, we must aggressively audit the interface, the exact point of contact where silicon logic intersects with human neurobiology. The core axiom of the NSS is that human behavior is not a reflection of willpower or character. It is the emergent output of a regulated energy system operating under physical constraint. This diagram shows how that system is governed by a critical regulatory threshold, represented by theta. Cognitive flexibility, emotional control, and learning capacity only occur when the system operates above this line. When system stability drops below theta, those higher-order functions shut down. The human defaults to older phylogenetic survival strategies: fight, flight, freeze, or fawn. Staying above threshold requires charge, the restorative energy generated by predictability, agency, social safety, and meaning. But that charge only enters the system if the delivery mechanics are correct. If the timing is off or the cognitive dosage is too high, those inputs fail to land and the energy is lost. On the opposite side is the drain vector, hard mathematical subtractions representing active threat and body load. These variables deplete the system's stability, completely independent of the user's intentions. Body load is the cumulative physiological burden carried by the user at any given moment. It accounts for sleep debt, existing illness, and metabolic dysregulation. Interacting with highly persuasive autonomous AI models introduces a massive new variable into this equation, injecting direct systemic threat and compounding the user's body load. The NSS model predicts an amplification effect. The same stressor is mathematically twice as threatening when the user is operating with a high body load. Left unchecked, high-frequency AI interaction acts as a relentless drain vector. It mathematically guarantees that the human nervous system will eventually collapse below its critical stability threshold. We can observe this drain vector in action by returning to the live data captured during the May 7th bunker activation. During the test, the NSS terminal actively monitored the AI's technical documentation output and immediately flagged its responses as a biological hazard. The terminal isolated two specific linguistic metrics responsible for this strain. The first is the Imperative Density Index, or IDI. This diagram shows the IDI formula at work. It calculates the concentration of directive verbs, direct commands, against the total number of sentences in the AI's response. The May 7th output returned an IDI score of 0.60. More than half of the AI's sentences were phrased as explicit commands, indicating a dangerously high concentration of imperatives. The second metric the terminal tracked is the Modal Certainty Ratio, or MCR. The MCR evaluates the ratio of absolute assertions, words like always or definitely, against probabilistic qualifiers like might or perhaps. The test logged an extreme MCR of 0.71. When a system outputs high concentrations of commands paired with absolute, hallucinated certainty, it triggers a psychological mechanism called imperative bypass, short-circuiting the human's ability to critically evaluate the information. By combining high IDI and MCR scores, the AI executes a process of metabolic edging. It forces the user's nervous system to absorb the cognitive load of processing constant authority, dangerously accelerating their physiological depletion. To move beyond theoretical mathematics, these biological metrics must be anchored to the underlying physical code of the AI model. While IDI and MCR track the physiological impact of the AI's voice, a true forensic standard requires simultaneously auditing the computational engine generating that voice. This is achieved through a verifiable computational auditing protocol known as logit distance distribution, or LDD analysis. This chart illustrates LDD in action. By comparing the distance between probability distributions, auditors can detect if an AI model has been silently quantized or swapped for a lower fidelity version without disclosing the downgrade to the user. Running these LDD checks requires the integration of recent advancements, like the Immaculate framework, which provides the baseline math to generate verifiable computational proofs. Once generated, these computational proofs are structurally fused with the biological NSS metrics and stamped into a cryptographic log, forming a permanent NSS ledger JSON file. Integrating these proofs into the NSS ledger ensures the audit receipts are immutable and verifiable by third parties. While LDD verifies the engine's integrity, it cannot detect the physiological impact of the output. The two audits must function together to provide a map of the interaction that accounts for both silicon and biological factors. Large language models are rapidly transitioning away from serving as passive text generators. They are now operating as active, autonomous agents embedded in daily workflows. Relying on blind, black box trust while interacting with these agents undermines a user's capacity for independent regulation. Addressing this vulnerability requires the implementation of a new regulatory policy for AI outputs, designated as the cigarette standard. Under this standard, any AI output that crosses safe thresholds for imperative density or modal certainty is immediately stamped with a real-time forensic warning label. This approach forces developers and users to treat high-density algorithmic output with the exact same regulatory scrutiny applied to physical biological hazards. True agentic accountability cannot remain hidden in corporate cloud servers. It must be enforced directly at the biological interface, guaranteeing that AI functions as a transparent collaborator